Welcome to my YouTube channel Cognara. I'm Michael, your science and technology educator. Today, we are going to explore one of the most misunderstood and fascinating questions in modern science. Is time travel actually possible? Not in movies, not in science fiction, but within the real laws of physics as scientists understand them today. When people hear the words time travel, they imagine machines, portals, flashing lights, and dramatic jumps into the past or future. But real science approaches this idea very differently. It does not begin with imagination. It begins with time itself, and more importantly, with how time behaves when we look at reality closely enough. To understand time travel through quantum physics, we must first accept something uncomfortable. Time is not as solid, stable, or universal as it feels. In everyday life, time feels simple. Seconds pass, minutes follow, and yesterday remains behind us. But physics has shown us that this experience is not the full story. At deep levels of reality, time behaves in strange and sometimes counterintuitive ways. This is where quantum physics enters the conversation. Quantum physics is the science of the very small. It describes how particles behave at scales far smaller than atoms. And at this scale, the rules of reality begin to bend. Particles do not behave like solid objects. They exist in probabilities. They can be in more than one state at the same time. They can influence each other instantly across distance. And most surprisingly, they do not always follow time in the way we expect. Before we talk about time travel, we must talk about what time actually is. In classical physics, time was once considered absolute. It flowed forward at the same rate everywhere in the universe. But this idea collapsed in the early 20th century when Albert Einstein introduced the theory of relativity. Relativity showed us that time is connected to space, forming a single structure called spacetime. Time can slow down. It can stretch. It can behave differently depending on motion and gravity. This alone already gives us a form of time travel. Astronauts on the International Space Station age slightly slower than people on Earth. Atomic clocks flown on airplanes tick differently than clocks on the ground. These are not theories. These are measured facts. So time travel to the future is already real, even if only by fractions of a second. But quantum physics pushes this idea much further. In the quantum world, particles do not always move forward through time in a clean, predictable way. Some experiments suggest that cause and effect are not always neatly ordered. In certain situations, the future can influence the past, at least at the quantum level. This does not mean humans can send messages back in time. But it does mean that time, as a strict one-way road, may not be fundamental. One famous experiment that challenges our intuition is the delayed choice quantum eraser experiment. In this experiment, particles behave differently depending on measurements made after they have already passed through an experimental setup. In simple terms, the decision to observe something in the present appears to influence how the particle behaved in the past. This does not break reality. But it does force physicists to rethink what time really means. In the quantum world, events are not always locked into a fixed timeline until they are observed. This leads to a deeper question. If time is not fixed at the smallest scales, then where does the sense of time flowing forward come from? Many physicists believe that time may not be fundamental at all. It may emerge from deeper processes, much like temperature emerges from the motion of atoms. At the deepest level, reality may not care about past or future. It may simply exist in a state where all possibilities coexist. This idea connects directly to time travel. If time is not fundamental, then moving through time may not require breaking the laws of physics. It may simply require understanding them at a deeper level. Quantum physics also introduces the concept of superposition. A particle can exist in multiple states at once until it is measured. This means that, in some sense, multiple timelines or possibilities coexist simultaneously. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that every possible outcome actually occurs in a branching universe. If this interpretation is correct, then traveling to the past would not change your original timeline. It would place you into a different branch of reality. This avoids paradoxes like the grandfather paradox, where changing the past would erase the present. Instead of changing history, you would be visiting a different version of it. This idea is speculative, but it is mathematically consistent. Another quantum concept tied to time travel is entanglement. Entangled particles remain connected regardless of distance. When one particle changes, the other responds instantly. This connection appears to ignore time and space. While entanglement cannot be used to send information backward in time, it suggests that the universe allows connections that are not limited by classical timelines. This again hints that time may not be the rigid structure we experience. Some physicists have proposed theoretical models where time loops could exist at the quantum level. These are called closed time-like curves. In such models, a particle could interact with its own past state without creating contradictions. The mathematics allow self-consistent loops where events influence themselves in stable ways. These ideas are not proven, but they are taken seriously enough to be studied. The biggest obstacle to time travel is not mathematics. It is energy and stability. Any structure that allows time loops would require extreme conditions, such as enormous gravitational fields or exotic forms of matter that may not exist naturally. Quantum physics does not promise time travel, but it refuses to rule it out completely. What it does tell us is that time is not simple. It is flexible. It is contextual. It may even be emergent. And if time is emergent, then our understanding of past, present, and future may be incomplete. At this point, honest science draws a clear line. Quantum physics suggests that time behaves differently at fundamental levels, but it does not provide a practical method for humans to travel through time. Yet, what it does provide is something deeper. It forces us to question whether the future is as open as we think, whether the past is as fixed as it feels, and whether reality itself is more like a vast network of possibilities rather than a single unfolding story. And this brings us to the most important idea of all. Time travel may not be about machines or movement. It may be about understanding what time truly is. If this exploration changed how you think about time, reality, and physics, share your thoughts in the comments. And for more calm, thoughtful, and deeply human explorations of science, technology, and the universe, subscribe to the Cognara YouTube channel. I'm Michael, your science and technology educator. And I'll see you again, here on Cognara.